Alright, this video is about similarity, and you will notice that we have some stuff from chapter 11 and some stuff from chapter 12 in the same video. They did similar areas in chapter 11, and they do similar volumes and 3D stuff in chapter 12. We thought we'd just throw them in on the same day. So yes, this is not a misprint. There's actually some stuff from two different chapters. Okay, first of all, are you able to figure out what congruent or similar solids even look like? And then let's talk about their properties. Similar, we used the word similarity back in similar triangles a lot. Actually, we had a whole unit on similarity right at the end of the first semester. And it was about things that were the same shape, but they were different sizes. They had all the same angles. We had a lot of stuff with similar triangles. There was triangle number 1. It was similar probably to triangle number 2. And we used this symbol for similarity, and all the angles were congruent. But the sides were not congruent. They were in proportion. And we had things like side angle side to prove one triangle might be similar to another, and the sides were proportional and the angles were congruent. We're not going to go into proofs and stuff like we did back then. But we are going to talk about that proportion thing. The proportion thing was really nice because it was a lot like what we're doing now. We use it to find lengths of things and make relationships numerically. Okay, so first of all, we're talking about three-dimensional things. There's a couple things that are always similar. If you had two spheres, the two spheres would always be similar. You have a ball here, and you have another ball that's bigger than that. They are the same shape. Any two spheres, gosh, it's hard to draw with this today, have to be the same shape, but they might be different sizes. They look like evil smiley faces. Sorry about that. Also, cubes. If you had two cubes, almost better drawing those, and a larger cube. If it's really a cube, and remember in a cube, all the edges are the same length. You know, whatever this length is different, but remember the ratio here is always going to be the same. It's always going to be A to B because these are always all the same in here, and these are always the same in here. So all the ratios are going to stay proportional. So spheres and cubes and really simple things like that have a lot of kind of internally referenced same lengths are probably always going to be similar. But for this other stuff that we're normally dealing with this unit, the prisms and the pyramids, we got to make sure that everything there's a lot more similarity going on. So by definition, what we're saying here is if those two solids are similar, we're sure that the bases are similar and all the corresponding sides are proportional. Okay. Oh, and of course, if anything's congruent, of course it's similar, but it's kind of boringly similar because the scale factor is 1 to 1. All right, so here's two similar areas in general. Now this is like taking what we learned with triangles and just making it one step more generic. If these two things are similar, we know all the angles are congruent, and we know that there's this one kind of common ratio that's going to make everything the same. Like this length AB divided by FG is the same as BC divided by GH is equal to DC over JH, that kind of stuff. But the new part here is now, since we're talking about area, what does that mean in terms of area? So the area, the blue area compared to the green area, isn't the same fraction, but it's that fraction squared. What do we mean by that? Well, let me make a couple similar rectangles down here. Let's say this length is 3 and this length is 5. And let's say it's similar. Oops, sorry, fast forward, rewind. Here I'm back. Okay, let's say we've got similar rectangles here. Here, this one's 5 by 3, and let's say I'm trying to solve for that one over here. Back in the old days when we were doing similar triangles, we would say something like, well, 3 is to 6, like 5 is to x, and we would solve this for proportions. We're looking for a length. You'd say, well, 3 over 6 equals 5 over x, so 3x cross multiply equals 5 times 6, which is 30. So we could figure this out, and we would find out that x is 10. And you probably could have done this by eyeball, realizing that, oh yeah, these rectangles are twice as long as they are. Or sorry, this was a scale factor 2, so this is a scale factor 2. And basically that's what we're dealing with when we do those proportions. But when we're talking about areas, the areas aren't going to work out like that, because look at the area of this thing. The area of this is 15, and you might think that the area over here is just going to be twice as big. Well, it's not. What's the area of a 6 by 10? 6 times 10 is 60. Whoa, are you freaking out yet? This is 15, this is 60. What's going on here? Because we just sort of figured out, like, you can tell by looking at this that these sides I have to double to make them this big. So let me rewrite this here. Just like how this proportion worked. I'm just running out of room here. I could take any one of these lengths and multiply it by 2, and I'll get that times 2. Same thing with 5. 5 times 2 is 10. it's proportional. So any of the lengths, if I multiply it by 2, that's great. But what we're saying here, because there's this little square here, you can't take the area times 2 to get the area. It doesn't work like that. You have to take it times 2 squared. So it's like saying we have to take it times, it's like saying we have to take it times 4. And notice 15 times 4 is actually 60. So this is kind of like a jump to a new dimension. We are used to doing this ratio of sides. Well, we need this ratio of sides. We need to use the 5 times 2. This is an important number. That we're going to call, usually we call that K. That's the ratio of the sides. But this ratio of the areas, well, areas don't compare quite the same way. Areas compare like K squared. Okay, we'll do this a bunch more. Oh gosh, but right now we have to jump to volume. So if the ratio of the length is K, the ratio of the areas is K squared, maybe you could have guessed this by now, the ratio of these volumes is going to be K cubed. So I'm not going to take the time to find the volumes of these pentagonal pyramids, because quite frankly, that's a lot of work. But the way this works is, let's say this length is actually 2 and this length is actually 3, and everything about these is similar. So this is just a blown up version of this. It's just all together, like all the lengths are 50% longer. So if this is 2 and this is 3, so I took everything in here and multiplied it by 1.5, or I took all the 2's here and they became 3. So the scale factor is 2 to 3. The ratio of surface area is going to be 4 parts to 9 parts, and the ratio of volume is going to be 8 to 27. Another way to say that is that if you're taking a length here, you could multiply it times 1.5. That's not a good time symbol. Okay, so in one of the lengths, you could take times 1.5. So I would say 1.5 is the K here. Actually, 1.5 is another way to say a 3 to 2 ratio, right? Because 3 over 2 is 1.5, right? I like my K's to be bigger than 5, or bigger than 1. Sorry, bigger than 5. Bigger than 1. You can make them that way. If we said it this way, if the ratio K is this times 1.5, then K squared, that's the way we compare volumes. That's 1.5 squared, which is 2 1/4. And what's K cubed? Oh gosh, K cubed I have to do in my calculator. Oh, let's talk about how to do cubes on the calculator. To do K cubed, to do 1.5, oh, you can't see this. Can I make this smaller? Sorry. That's better. To do 1.5 squared is no big deal. You just do that, right? But to do 1.5, sorry, to do 1.5 cubed, you do 1.5, and then it's, oh, you can't see the calculator buttons. It's this button right here for to the power of 3, and I get that number, so it's like 3.375. Let's go back to this. 3.375. If I took all these fractions, 9 over 4, and 27 over 8. If I made those into decimals, these would be the decimals. They would be, this ratio is 3 to 2. This ratio is 9 to 4. This ratio is 27 to 8. And that's how the volumes compare. So this volume is 9/4 times bigger than this volume. Oh, I'm sorry. Oh, I messed that up. Oh, I'm glad I caught it before I let you go on believing that. The lateral area of this is 9/4 times bigger than the lateral area of this. And the volume of this is 27/8 times bigger than the volume of this. All right, I'll do some actual problems before I get myself in more trouble. All right, stuffed animals. I have no idea the volume formula for a stuffed animal. It's not on your sheet. But, okay, I'm going to try to draw. You know what? I'm going to borrow these from the internet. I'll be right back. Pandas. Okay, so I went to the internet and I borrowed some stuffed pandas. And again, I don't have a formula for the volume of a panda or the surface area of a panda. But they tell you this. They tell you the bigger one has a height of 16. And the smaller one has a height of 12. The smaller one needs 40 square inches of material for its surface area. So surface area over here is 40, and our question is find the surface area over here. Okay, so what we'll like to do is figure out what does this 12 have to get multiplied by to make this 16. This 12 is a length. It's how far that is, and this 16 is a length. It's a linear measurement. It's one-dimensional. It's things like inches. And we need to translate from inches of similarity to square inches of similarity when we're talking about area. So let's figure out what that fraction is. What did this have to get multiplied by to turn into that? Well, it was 12. It turned into 16. So I like to do it this way. Length divided by length is K. I like to put the bigger one on top. You can do this either way. You just have to be consistent. I'm always going to do it this way so that we are consistent. 16 over 12, that reduces to what, 4 over 3? Okay, so this panda is 4/3 taller than this one. That means it's not going to be, I mean, don't get sucked into this trap. It's not just going to be 40 times 4/3 becomes the surface area. No, I need to use k squared as the translator for how areas talk to each other. So k squared is going to be that number squared, which is, believe it or not, 16 again. But now it's over 9. So this surface area is 16/9 as big as 40. How do I write that? Well, I just say that again. It's 16/9 as big as 40, and that equals, there we go, 40 times, I like doing it this way, 16/9, if you want it as a fraction, which I love, 649ths, or it's about, now might as well do that, 649ths, whoa, there's all the stuffed animals I was trying to find. All right, that was my search page for stuffed animals. 649ths, or if you like decimals, 71.1, repeat it. Okay, yeah, so that's how we do that. We found the k factor for how lengths compare, and then we need to use k squared to multiply small area to get big area. Not always that easy. I know that seemed like it may have been hard, but that's actually one of the easier examples. Are these things similar? Well, if they're similar, all the lengths are going to have to be proportional. So 10, when we multiply 10 by something, it's going to have to be the same thing, to get 15. It's going to be the same thing we have to multiply 8 by to get 12, and 6 to get 9, and 8 to get. So all these fractions are going to have to be equal. 10 has to go with 15, like 8 has to go with 12. There's actually 2 of those, but they're already the same, so I don't have to worry about more of that. And how 6 goes with 9. Are these all true? I think they all equal 2/3. So I think we're okay. I think all those figures are the same. Now, we don't really know that all the angles are congruent, but I think we can be pretty sure that they are. Yeah, great. Given that these are similar, find the length of this side. And all I know about is area. This stands for unit squared. I know the ratio of areas. The ratio of areas is 72/50. And I'm going to label that as a ratio, but not just call it k. Remember, this is a ratio of areas. So this actually is k squared. This is how the areas compare. So I need to treat this as k squared. Let's reduce that and maybe even square root it. Where am I going? 72/50. So the square root of 72/50 is really 6/5, perfectly 6/5. Okay, so so that means, and I was finding the square root there. So k, that tells me k is 6/5. So as the square root, just so you can remember this, as the square root of 72/50, that's k. It's 6/5. So when I translate from here to here, this needs to be 6/5 as big as this one. So this is just going to equal 7 times 6/5. It's 6/5 larger, which is 42/5. I don't think I'm going to finish this video in time. I might as well stop here before I get myself in trouble. This is 8.4. Okay, it's a little bit different. Let me just say this while I have a minute here. This is a little bit different than doing everything by proportions. Like, you can't really just, I know you want to do this. I know you want to go x is to 7 as 72 is to 50th. This won't work. You can't do that because it looks like I'm making cross multiplying there. No, I'm not. I'm crossing that off. That's not possible because on this side, it's like we're talking on 2 different channels here. This is about how lengths compare. This is about how areas compare. It ain't going to work. Okay, I'm just going to pause here because I know I can't get done in the next minute and a half. I'll see you in the next part.